Sorry, guys. Okay, so right. So we looked at the definition of inner product, right? So let's quickly review what this was. So we said that an inner product is basically going to take an ordered pair. So it's going to take vectors u, v, right? And it will give you a complex number meaning, sorry, a number in the field, right? So it takes two vectors and it gives you a way to combine them in some way and gives you a complex number or a whatever number in the field. And it had these properties, right? So let's quickly review them. So the first property was that if you take the inner product with the same vector with itself, right, this is going to be non-negative numbers. That was one. Second was that if this turns out to be zero, if you take the inner product with itself and it's zero, then it means that the vector itself is zero. And that was the second property. The third is that you have additivity in the first slot. So if you write u plus v, you can split it down as the inner product with u first plus the inner product with v, right? And then we had homogeneity. Oh, I forgot to check the pronunciation. Anyway, so this is just saying that if you have lambda in the, so if you multiply the vector with a scalar, you can bring the scalar out and take the inner product with the rest of the vector. Okay, so that was the second property, and the last one was conjugate symmetry. So uv was the same as vu, but with a complex conjugate. Okay. So does anyone remember, or can anyone see why it was enough to require these two properties in the first slot and not the second slot? Right? So because we have this conjugate symmetry property, so it's redundant to require the other ones. What were the letters? R. Is it okay? S already answered L. Is it okay? Yeah. Just let me keep this started again. Yeah.
So property number 3 and 4, additivity and homogeneity. They're in the first slot, both will be together in the first slot. And the second slot will come together. We are applied to the second slot. How do we find it?
Yeah. So the idea here is that you have u plus v acting on w, right? So here we have the property that, so you can ask, right? You can ask, what if it was this way, right? What if it was w and you had u plus v on the second slot? I didn't say anything about that part. Right? So I was saying you can use this last property to convert this. You can take the conjugate, right? So this would be the same as the conjugate of u plus vw, right? And then you can compute these guys. So you can do u plus w, you can do it in the conjugate, and right? You can do this. So that's all I was saying. Good. Any other questions? Wait, what is your initial? What is your initial? What is your name? Wait. Okay. Is it okay if I ask you every now and then if things are making sense? All right. So this is fine. And then we said that, so we looked at a few examples, right? So we looked at, so the standard example is that you just take the first element. So if you have vectors in Fn, you take the first component as it is, the second is a complex conjugate, you sum them. This was like the standard thing. And this we are going to use a lot, okay, so it's worth reviewing. And then we talked about inner product spaces, and these were just saying that it's a vector space along with an inner product defined on this vector space. Okay, so far we have caught up. This is all that we had done in the previous. Inner product space is just saying you have a vector space and you have a notion of inner product defined for the vector space. There's nothing really deep. So that's what, because normally when you're defining a vector space, you don't need to necessarily also define the inner product, right? You can define a vector space independently. Okay. All right. And the most important example of an inner product space is Fn. Okay, so Fn with Euclidean inner product. So Euclidean inner product is exactly the one that I described here. This is Euclidean inner product. Okay, so if you have W1, W2, Wn, and you take an inner product with Z1 to Zn, this is just going to be W1, Z1 bar, and so on. Okay, so this is the Euclidean inner product. All right. The convention that we're going to follow. Okay. Okay, so the convention we're going to follow here is that if I'm referring to Fn, okay, and I do not mention the inner products, like what form, what definition I'm using, you're assuming that it is going to be the Euclidean inner product. Okay, it is just a convention. Nothing very deep. Yeah? Okay. Yeah, so this is just saying that this is the notation for the rest of this chapter. V denotes an inner product space over F. So if V is Fn, then we know that it's a Euclidean inner product. And for the rest of this chapter, when we talk about a vector space, we are implicitly going to assume that it's an inner product space. That is all it is. So we'll not say repeatedly that, V is an inner product space, V is an inner product space. That's it. All right. Yeah, this part I think we can skip for now. Let's move on to proposition 6.7. So now let's do some nice things, right? So these things I sort of already alluded to, but let's look at some basic properties of inner products. Okay. So the first property says that you pick any fixed q. Then the function that takes v to v comma u is a linear map v to. Is the statement clear? Okay, you can think of it as a map, right? I give you two vectors. It is taking those two vectors and producing a number, right? So you can think of it as a map, and sorry, a linear. You can think of it as a map, and the claim is that this map is linear. So we'll prove these things in a moment. The second one is saying the following. So if you have 0 and you take an inner product with some vector, it is going to give you 0 for all vectors in the vector space. So we didn't explicitly say it, right? In the properties, when we define the properties of inner product, right? We did not explicitly say anything about what happens when you take one of the vectors to be 0, right? So we have to deduce it from the properties. Is that is that okay? Yeah. Okay. All right. So that is the second statement. The third statement is, of course, the converse, right? Converse meaning like you flip the slots. This I guess you can already answer from the discussion we just had. This one should also be clear. I think I already essentially proved this, right? That so we had u plus v on w is the same as uw plus vw. Okay. This statement is saying that if you have uv plus w, you can write it as uv plus uw. Right? So this is going to follow from the conjugation property that I just said. Okay, we'll see the proof nonetheless, but that's the idea. The last one is saying what? So the last one is saying that we had lambda u v is the same as lambda times uv, correct? So in the first slot, when you had lambda, you could pull it out. This thing is saying that if you have lambda in the second slot, so it's saying if you have u lambda v, then you can write it as lambda bar uv. Okay, so now you pick up a complex conjugate. It's a small thing to keep in mind. Okay, so it depends on the definition, where you're getting the complex conjugate. All right. So look at the proofs. So for the first one, we have to show linearity, right? Okay. So for linearity, okay, so these are the properties. Again, this is the definition of inner product. So I have inner product definition. I've just copied what we had already written. Okay, just for reference. So what do we need to show for a map to be a linear map? We have to show that for a fixed u. So remember, u was fixed. Okay, and this was the argument, right? So we need to show that. So how do you show a map is linear? So f. So if you remember your Hoffman influence, we said alpha plus c beta has to be the same as f alpha plus c times f beta, right? This used to be the definition of what it means to be linear, correct? Okay, so now what we're going to do is we're going to apply this. So our function now is what? The function is, so f of alpha is now defined to be comma beta. Okay, so beta is the fixed vector and alpha is your argument. Is that okay? Making sense? Is it making sense? S? Okay. L? Okay. So now, we're just going to apply this, right? So we take the so B is the first vector, A is the scalar. So this is the first vector. This is the scalar, right? And this is the second vector, correct? So now we can use this property, this additivity in the first slot, right? So we use additivity. This A will still be inside when you use the additivity property. And then which property do we use to get A outside? tell me which property that these are named, right? Here you can read them, right? Or is it too small? It's too small, okay.
That's a bit I can see. You can use the ideal property to say that f alpha plus c beta to split into f alpha plus c beta.
Exactly. And then how do you get the c outside? You need one more property. Exactly. Exactly. Is that okay? Does it make sense? So what I said was, you know, so here we skipped one step, right? So let me write the step here. So how do we do this? So we start with v plus awu, okay, and then this is equal to vu plus awu, right? And then we use this homogeneity property to pull out this. Is that okay? Very straightforward stuff. Nothing very complicated so far. R S. Okay. No. If it's going too slow, also you can tell me, okay? Because I have no idea. So if it goes slow, tell me. All right. So this part is fine. So this A part is done. Any questions about the A part? It's okay. All right. What is the B part? So B part is saying that you want to show that if you take the inner product with a zero vector, you will get zero regardless of which other vector you pick, right? So let's see how this is done. So here it just follows from the fact that you have a linear map, right? So a linear map, we remember, would send a zero vector to the numbers, okay? Why is that? Because you can basically just say that, you know, if I have, so suppose you have f of u, sorry, if you have f of zero vector, this you can write as f of zero times some vector v, doesn't matter which, and this would be zero times f of v. This would be zero. Okay? So it's basically following from the homogeneity property, if you really want to. Any questions? Okay. So the second part is also fine. Yeah. Okay. So let's look at the third part. Third part is, I mean, these I think we already established, right? We're just using the conjugation property. You want me to do them? Is it completely clear, everyone? Is there anybody at all who wants to look at the proof there? Okay. So then we can continue. Yeah, I mean, it's just a few lines. Okay, you can look at the text. It's just you're using just those two properties, homogeneity and whatever, either additivity for this one or the sorry, you're using conjugate symmetry in conjunction with either the homogeneity property or in conjunction with the additivity property. That's all you're doing. Okay. All right. So we can continue then. So now let's look at norms. So we've understood inner products to a certain degree. So one of the reasons we defined the inner product, remember when I was motivating this, was so that we can have some kind of a linear map that relates well to the norm of the vector, right? To the length of the vector. Right? That is why we started with the dot product. And then we said when you take the dot product with itself, it will give you the length of the vector. So now we are going to use the same analogy and to describe the norm instead of the length. So we're generalizing that idea of length. Okay? Well, yeah. So norm is defined to be this object. So the norm of a vector v is defined to be the square root. Okay, so let me write. So norm of a vector v is defined to be. So this is the symbol we use. Okay, so this is the symbol for norm. And it is defined to be square root of the inner product with its section. Is the definition of it? It's reminiscent of what we did with the. Is that okay? Is the definition making sense? Okay. So now let's look at an example. So the first example is, of course, with Euclidean space. So let's see if we can reproduce the result that we had, right? So the dot product, remember, was what? It was if you have Z1, Z2, Zn, you took the inner product with itself, right? This was giving you. So okay, no, let me write it properly. So the length of Z1 to Zn. This is your vector. The length is defined to be what? Z1 square plus Zn square. So suppose these are real, okay, for simplicity. Okay, if all the components are real, then this is how we define the length. Right? Geometrically, this is what we do. Correct? So now here, when you have Z1 to Zn arbitrary, if you use the definition for lengths from this definition of a norm, it would be the square root of inner product of Z1 to Zn within Z. Right? And what was the inner product we said we would use? The inner product we said we would use is Zi bar, sorry, right? And then the square. Correct? Yeah. Yeah, so I think for when you're defining fields, I think we did define inverse elements in the field, right? There was a notion of mathematical inverse, and I think it should follow from the properties of the field. Like the field should have some notion. But for now, you can assume that the field is complex. I think for this part of it, we can assume it's complex, but in general, the field will define some notion. Okay, that is my understanding. I may be slightly wrong, okay, because I remember that we had a notion of inverse, but now this is like a fraction, right? It's -1 by half, potentially, or power half. So maybe there is something. Yeah. For now, we can assume it's complex. I can double check and tell you. That's a good question. So the question was, does the field? I think it should, but I need to double check. Does the field in general define square root? Okay, that's a good question. I'll check it out. Okay. Any other questions?
Could you repeat what the question was asked?
Well, the question was, we're using the square root here, right? And when we define the field, I forgot the exact definition of the field, but I remember that there were like inverses and things.
Yeah, right.
But whether there was a square root or not is I don't remember exactly. So maybe it follows from the definitions. I'll have to check. Okay? But for now, we can assume it's complex numbers. Okay. Any questions? Good. All right. Okay, so that was the first example. The second example, which is actually kind of nice, which we would probably use as as a sort of non-trivial definition of an inner product, would be this. So we had this. So we said that if you have, say, polynomials. So suppose you have Pn on real numbers. So Pn is the set of polynomials, okay, of at most degree n on the reals. Then suppose P and Q are two such polynomials. We define the inner product in one of the examples as the integration from -1 to 1 of PQ dx. Okay. So this is how we define the inner product. And then using this definition, we can define the norm of so to define the norm of Q, right? What do we write? We will write it as square root of the inner product of Q with itself. Okay. So don't get confused. Okay, it's just all a matter of what the definition is. Is that okay? Making sense? All right. So
Why is the interval not square?
you can have whatever definition you want. This was because we were using, so see, you see, right? So in the vector space of continuous real valued functions on -1 to 1 with inner product given as in part C of this example. So in part C, so this was this example we looked at last time. Okay? So it is just the definition of the inner product. Any questions otherwise besides this? Is there a question? All. Okay, so right. So now let's look at proposition 6.10. So proposition 6.10 says the following. It says suppose V is a vector. Oops. Suppose V is a vector. The length of V is 0 if and only if the vector itself is 0. Okay. So can someone see the proof? So let's look at it together, right? So the norm of the vector is what? Norm of V is, what is the definition? We just looked at the definition. It's the square root of V, right? Okay. And then remember there was a property, right? We said that VV is 0 is equivalent to V being 0. Right? So you sort of see the proof. Right? L is the proof making sense? So, yes. All right. So this one is fine. The second statement is saying what? It is saying that lambda V is the same as lambda times the norm of the vector, right? For all lambda. That is the statement. So let's see how we might approach this. So let's write it out. So lambda V. So I'm just writing down the stuff over here. Okay, I'm writing everything so I don't go too fast. That's true. Actually, when it's just on the screen, it's easy to go fast. So let's just write it down. So lambda V. Right, this is just the definition, right? Because we have the square here, we remove the square root. This step is okay. Yeah. Then we can get one lambda outside using the homogeneity property. That is fine. Okay, and then we can also get the other lambda out, but with the lambda bar, right, from the conjugate property. So you'll have lambda bar, we circle. And then lambda bar is what? It's just a complex number, so we can write it as the length of lambda square or the normal. Okay, and then we are left. And this is what? This we can write as the norm of the vector squared. Right? So we get the claimed result, right? So you have the square here, you have both terms squared here, so you get lambda V is the same as norm of lambda times. Right? Is that right? Is it good? Okay. So now let's look at definition 6.11. It says, so you consider two vectors u, v in V, okay, are called orthogonal. Okay, so these are orthogonal if inner product of u and v is 0. Is the definition clear? Yes, orthogonal vectors are just you look at the inner product, if it should vanish. That's it. That's the definition. Okay. All right. So to start with, we look at a simple result here. So the result we look at is orthogonality and the zero vector. So it says that the zero vector is orthogonal to all vectors in V. Okay. So first statement, okay. All right. So we'll prove it. We haven't proved it yet. But let's see how we would prove it. Right. So to prove this, what do you have to show? You have to show that 0, v is 0. That's the definition. Okay. So this is not clear. But then remember this we just proved, right? We said, how did we prove it? We said that this map is a linear map, right? And linear maps end 0 to 0. Okay, so this is actually true. Yeah. Okay, so the first part we already proved. The second part says what? So 0 is the only vector in V that is orthogonal to itself. Okay. So what does that mean? So we have to say that, so suppose if V is some arbitrary vector, okay. For a vector to be orthogonal to itself, what should be the condition? Right? So if a vector is orthogonal to itself, what does it mean? V, the inner product is 0. Correct? And what did we do? We proved that this is if and only if for inner products when V is 0. Correct? That was just from the definition. That's it. Okay. So we also proved this part. Any questions about the proposition? Okay. All right. So now let's look at the special case when V is R2. Okay. And in this case, this theorem, when you restrict V to being R2, which is 2 dimensions, it's saying that this result is known for 2,500 years. So it's a very old result. It's the Pythagoras theorem. We all know this. But now what it's doing is it's stating it in generality. So it is stating it for arbitrary vectors. Okay, not just R2. So it can be R3, Rn, or even C, whatever. It doesn't matter. Okay. All right. So And obviously the proof that we're using is not the original one because you have to introduce all this machinery to be able to even make such statements. So these didn't exist back in the day. And the statement is, of course, we are very well familiar with this. So if you imagine that there is some vector u and there is some vector v, okay, and we are given that u and v are orthogonal. Okay, so the inner product of u and v is 0. Okay? So if you're given these two things, then the claim is that the norm of u plus v is going to be the norm of u plus the norm of v squared, each of them squared. Okay, so let's see how to prove this. It's extremely simple, so it's good to just try to do it directly. So u plus v mod square. So how will we write it in terms of an inner product? Just apply the definition. Right, so it's u plus v, right? And now we can use all our favorite properties about linearity and stuff, right? So let's do it one by one. So you have u plus v plus v u plus v, correct? And then this we can further expand as u plus. But the point is uv is 0, right? So uv is 0, which is the same as vu, right? So we know these two things are 0. So we don't need to write the cross terms, right? So in the first one, I'm not writing the cross term with v, and the second one, I'm not writing the cross term with u. So you'll have v. Have v common. Is that okay? And now we can use the definition of the norm again. Right? So what would the definition tell us? Okay. And similarly for this, it would give you, correct? Fine. The proof is okay. That's just the statement. L. Is it making sense? Okay. All. Any questions? Anyone at all? Okay. All right. So now we continue. So suppose u and v are vectors such that v is not 0. Okay. So we want to write u. Okay. So suppose, yeah, okay, I started doing the same thing. So suppose that u, v are vectors and v is not a 0 vector. Okay, so that is the starting point. And what we want to do is we want to write u as a scalar multiple of v plus a vector w orthogonal to v. Okay, so let's draw the picture. Okay, so the picture would help. Actually, we already have a picture. So suppose you have some vector u. Okay, so there's some vector u, okay, and you're given some non-zero vector v. You're given some non-zero vector v. We want to write u as a combination of some scalar times v. So basically along the same direction, right? So some scalar times v. So let's call it cv plus a vector w that is orthogonal to v. Is it clear what we're trying to do? Yeah, is it clear? So you have a vector u, you have a vector v. You want to write u as some scalar times v, so it's in the same direction, plus a vector w, which is orthogonal. Okay, so that's what we're trying to do. So how might one do it? So let's just do it algebraically. Okay, so suppose that c is some scalar. Right? So c is the unknown, right? We don't know what c is. So let us just say that we write u in exactly the form we want. So it is some scalar times the vector v, right? Plus some other vector w. Okay. So what can we do? We can write it as u minus cv. This is fine. It's just we're canceling things. There's nothing I need. That is all. Okay. And what is the other condition we want, right? So this is some vector w. It's not some arbitrary vector w. We want this vector w to be orthogonal, right? Orthogonal to v. How do you do that? What is the definition of orthogonality? W. Exactly. So the inner product of w and v, we want this to be 0, correct? Okay, so now let's expand this. So this would be u minus cv inner product with v. It should vanish, correct? Is it making sense? Yeah. Okay, so now let's expand this. We can use all the nice properties we've learned. So this would be c v times v 0. Is that okay? Just simple algebra. And what was the unknown in this equation, right? So the unknown was C and W. These were the two unknowns. But notice that if you figure out C, you also fix W, right? Because the only thing to fix W was C, right? Everything else was already fixed, right? So now this C we can evaluate, right? So the C is just the inner product of U with V, okay, divided by the norm of square, correct? Is that okay? So a priori, it's not clear that you could have been able to do this, right? It's not obvious that you could do it. It turns out you can. So we just said, okay, algebraically we'll impose this condition, and it turns out you could solve for C. So therefore, this property is that okay? Okay. So how would I write the vector W now that we know C? Anyone? We just substitute C here, right? That's all we have to do. So we get the vector. So the vector is minus. Is that okay? That's just the definition. Right? I didn't do anything. I found C and then I substituted it back here. That's all I did. Okay. It's completely straightforward. Okay. So therefore, how we can express this vector U in terms of some scalar times V and an orthogonal vector is exactly like this. Okay, this is what we just did. I'm just substituting for C using this expression. Clear? L? With what's the name of the person behind you? What's your initial? The one behind you? Yours also. What is your second letter? M? Okay, M. M. Is it here? Okay. Follow it. Okay. So one can verify that. Okay. So one thing you can actually check explicitly. So this is the vector that we call W, right? And we wanted this W to be orthogonal to what vector? V, right? So one can actually check now that you've substituted it, that WV will turn out to be 0. That's how we found C. Obviously, it will, but you can check. Okay. Good. Making sense? Okay. Sure. All right. So now we basically summarize what we just said into a proposition. So we're saying, suppose UV are a vector, V is a non-zero vector. So you define C to be the inner product between U and V, and W you define to be U minus UV upon V square. I forgot a V here, times V. Okay. And then U is CV plus W and WV is 0. Is this clear? Okay, all the discussion we had is exactly just summarized. Nothing common. Following it. Okay. Okay, shall we move on? Okay. Okay. So the orthogonal decomposition above will be used to prove what we call the Cauchy-Schwarz inequality. Okay. And the Cauchy-Schwarz inequality happens to be very useful. If you pursue further studies, you will see it pops up almost everywhere and magically shows things that you want to show. So we'll just state it in a moment. Oh yeah, okay. Let's just state it. There's nothing else. I thought there was something else to say. So the statement is the following. So suppose that you have two vectors. So suppose U and V are vectors in the vector space capital V. Then the statement is the following. The absolute value of the inner product of these two vectors, okay, is going to be at most the norm of the first vector times norm of the second vector. Is the statement clear? Yeah, that's a very straightforward statement. Okay. And additionally, you have an inequality here. The question is, when does this inequality become an equality? So it's equal if and only if U is a scalar multiple of V or the other way. Okay. Is this clear? Okay, note that these statements are so these two things, you don't have to say the other way if both vectors are non-zero. Because if one is a scalar multiple of the other would be. But if one of the vectors is 0, then these statements are different. Okay. Just if you only know one vector is 0, then you have to be a little bit. Okay. All right. So let's continue then. All right. So here's the proof. So if V were actually 0 in this statement above, then there is both sides become 0, correct? Because so remember we proved this, right? It's a linear map, so this would give you 0, correct? And if you have the norm of u times norm of v, and if this quantity is 0, of course you'll get 0. Okay, so the first step is 0. Okay, is it okay? Yes. Yeah, we're just proving this. We're saying that this statement holds when v is 0. That's all we're saying. Okay. All right. So now let's do the non-trivial case, right? So suppose that v is not equal to 0. So suppose, yeah, let me make some space so I can write it down. Okay. So now suppose that the vector v is not actually 0. Now we'll use the proposition that we had. So using proposition 6.14. So this is the proposition, remember, where we were saying that you can express any vector as some vector along the same direction plus an orthogonal, right? So using that proposition, we can write u as inner product of u and v divided by norm of v times v plus w, where w is orthogonal, right? Orthogonal to v, correct? This we just proved. Is that okay? All right. Now we can use the how do you say it? Pythagorean theorem? Pythagorean theorem? I don't know. Let's use theorem P, my favorite trick. Okay. So theorem P tells us what? It tells us that you can write norm of u as the norm of this vector plus the norm of that vector, each element squared. Right? That's the Pythagorean theorem we prove. Okay, so this would be uv divided by norm of v square, v whole square plus norm of w square. Is that okay? Reasonable? Okay. All right. And now what do we have? We have uv. This is just a complex number, right? The inner product is a complex number, so I just do a mod square because it's the length of the vector using arithmetic. It's okay, right? I hope you're not getting lost. Okay, so I'm just saying that if you have c times some vector alpha and you do mod square, you're going to get mod square and then the vector. That's all I'm saying. Okay, so that's why we get this factor here. In the denominator, again, this was a complex number. Sorry, this was a number, so we multiply it twice because it's squared, and then you have the norm of v. Is this step okay? Right? Plus we have norm of w squared. So from here we can cancel norm of v squared, and what are we left with? We are left with, and this part uv is sorry. So this part uv is what appears in the statement, right? So it appears here in the statement of the Cauchy-Schwarz. So okay, so we have this, and now this is the positive number, and this is a positive number, right? So this is going to be at least as big as the first positive number or non-negative number. Is that okay? Making sense? Okay. And now we're essentially there, right? So now you have u v whole square is at least. Is that okay? Making sense? Right? Okay. And so this is exactly what we wanted to show, right? So if you look at the statement, so the statement was that this norm over here is at most the norms of each of the vectors. Sorry, this inner product, the absolute value of the inner product is at most the product of the norms of the vectors. This is what we get. Absolute value of the inner product is at most the norm of the vectors. Right? Okay, good. So we are essentially done with this first part. We still have to show the conditions about equality, right? When the inequality becomes an equality. So let's see how to show that. But before we do that, any questions about the first part? Is it making sense? Is it clear? Okay. All right. So now let's see how to show the equality aspect. So this part we are done with. Okay. So the Cauchy-Schwarz inequality becomes an equality. This is the most unfortunate thing about the English language that you have to say. Inequality becomes an equality, and it just sounds wrong all the time. Okay, so inequality becomes equality. I'll drop the article. Okay, so inequality becomes equality if and only if 6.16 is equality. Okay, so 6.16 was what? It was, so you see everything until the last step was equality, correct? It's only in this step that we have to introduce an inequality. Yeah. Okay. So for this last step to be equality, we basically must have that this W vector is 0, right? Because we know from the property of the norm that the only way that the norm of a vector is 0 if the vector is correct. Yeah. S. Wait, was it S? Is it making sense? So, okay. If something not here, tell me. Yeah. So this is equivalent to saying that the vector itself is 0, correct? Okay. And if the vector itself is 0, what do we conclude? We conclude that, so we had written U is equal to some scalar, so let's just write it as some scalar C times V plus W, right? And we are saying that this W has to be 0, right? This for this step to hold, we said that this norm has to be 0. If the norm is 0, that means the vector has to be 0. And if the vector is 0, we know that this U, which we wrote as, I'm just writing this part, right? So we wrote as some scalar times V plus some vector W. This vector W is 0. So what does that mean? That U is what? Exactly. Right? So U is just a scalar multiple of V, which is what the statement said, right? That U has to be scalar multiple of V. Or the other way. Or the other way, how do you do the other way? Because we assume that V is non-zero. To do the other way, assume U is non-zero. Okay? Make sense? L? Yeah? Okay. Follow. Okay, so this is fine. And then the conclusion is that the Cauchy-Schwarz inequality becomes an equality if, exactly as R mentioned, U is a scalar multiple of V or the other. Any questions about Cauchy-Schwarz? Is it clear? Yes. Uh-huh. Yeah. So the statement is that U is some scalar multiple of V. It's not that it has to be some fixed. It just has to be in the same direction. That is all that is being said. Did I misunderstand your question? I think I misunderstood your question. Say your question again. Wait, let me write down. So U is scalar multiple of V. Mm-hmm. Uh-huh. Yeah, it can be C prime, doesn't matter. So the point is that this scalar is okay. So this basically what is happening is that in this proposition 6.14, we are saying that suppose you have some vector U, right? And you had some vector V, okay? And we said that you can always write this vector U as some scalar times V plus some vector W, right? So if it were the case that U actually is, say, some C prime V already, right? Then that proposition would just give you that the W vector is 0 already, right? So it doesn't really matter. So this scalar that you're getting, this will become 1, okay? So the scalar here, so you, I'll give it to you. We can discuss it afterwards. But the point is that this scalar is exactly defined to be the inner product of UV. Okay, and if they're in the same direction, you just pick that scalar itself times the length. So it's automatically accounted for in the fact that basically there's a unique way in which you can write it. There are no, if you have two vectors like this, U and V, there would be some fixed unique scalar, right? We found the scalar explicitly. So it's not like you can write it as a, it's not possible that U is CV and U is C prime V. This is not possible. Because by linearity, then it would. It's not good. Is that okay? All. Okay, so for everyone else, the confusion was whether you can have like whether this scalar, this C could be fixed in different ways, essentially. But there's a unique scalar. So once you fix the vector u and v, there is a unique scalar that would appear. Okay? And if you want to think about it geometrically, it's actually a little bit easier. So if you have like two vectors, so if you think in two dimensions, u and v, it would be like basically this projection. Right? There's like cos theta, sin theta, something like so. It's essentially fully fixed. Okay. Any more questions? Okay. All right. Very well. So then let's continue. So now, okay. So here are some very cool examples of the Cauchy-Schwarz inequality. Okay. So the first example says the following. So examples for Cauchy-Schwarz. Yeah. So the first example is the following. So suppose you have x1 to xn and y1 to yn. All of these are real numbers. Okay. And I ask you, can you upper bound this quantity, xi, yi? Okay. So a priori, it's not so obvious, right? But it turns out that we can apply Cauchy-Schwarz. Why? Because this thing is what? This thing we can write as the vector x and the vector y, the inner product, correct? And it's just their mod, absolute value squared, right? And then we apply Cauchy-Schwarz. What does Cauchy-Schwarz tell us? That this thing is going to be at most norm of x times norm of y. I don't know. I forget the squares. Is it squared? It's squared, right? Oh, no, there's no square. Okay. In the statement, there's no square, but because now it's squared. Okay. Is this okay? So this is just Cauchy-Schwarz. Right? Is that okay? Yes? Yeah? Okay. And then this we can expand it. So what is the norm of x? Norm of x, remember, was xx squared. I always get confused with the. Yeah, I think it's right. And then the norm of y would be what? Norm of y would be y. No, the only thing I'm confused about it is as I forgot. So if you have a vector u, we write it as what? U, and then we had a square root, right? That is the definition. So when you write u squared, you will just write UG. My u looks like a v, sorry. Correct? So that's what I'm doing. So I'm writing the, right? This fine. And how do you write, what is xx? In a product of x with itself in the Euclidean norm. Sum over I, xi squared, right? Similarly for this one, sum over I. Is that acceptable? Right? Okay. And then you can plug them back in. And you plug them back in, what do you get? This thing is at most sum over xi squared times sum over y squared. Right? So we get this. Is that good? Clear? Yeah. All right. Now, if f and g are continuous, okay, so that was the first part. Again, it's sort of not obvious, right? A priori, it's not clear that this equation would hold. Okay? It's just a bunch of numbers. How do you know whether the product is going to be, that was this? And Cauchy-Schwarz very clearly tells you so. So the thing is that you have to be able to recognize the fact that something can be written in this inner product form. That is sort of the key thing that you have to be able to recognize when you see some expression. And remember, you have a lot of flexibility, right? Because you can have any vector space and you can have any notion of inner products. Okay, so the expressions themselves can look very scary, but if you can write them as an inner product of two vectors, you can immediately find them. Okay, so now let's look at a slightly more interesting example. So here it's saying suppose, so now, okay, so in this example, we're going to say suppose f and g are continuous real valued functions. Yeah, give me a second. Let me just make a little bit more space here. Okay. So suppose that f and g are continuous real valued functions, okay, on -1 to 1. Then and okay, so what do we want to look at? We're looking at -1 to 1 f of x, g of x, dx, mod square. Okay, this is the quantity we're looking at. Okay, now can anyone think of an inner product that we defined for such functions? Okay, so what do we want to do, right? So we want to write it as some inner product because f and g, they are in some vector space V, right? The vector space is what? That of continuous real value functions on the domain -1 to 1. Okay, so you can check that this is a vector space, first of all, right? Because the domain stays the same. So you can add a bunch of functions that will still give you another function. So this is a vector space, so that part is fine. Now we want to express this thing as an inner product of two different vectors, right? In this vector space, correct? That's what we want to do. Okay. And remember that there was this inner product that we had defined in the beginning, which said that FG, the inner product, is defined as the integration. Okay. Just like we were doing sums, right? So now it's replaced with integration because it's a continuous variable of fx times gx times dx. Okay, it's essentially the same as multiplying f and g and summing over all indices, except that you're doing it in continuous variables, right? Okay, so this is the inner product. Now, does this thing look similar to this? Right? So this is just saying what? It's saying that the inner product of fg mod square, right? This is what we have to bound. And how? What did we say? So Cauchy-Schwarz told us what? It told us that this can be written as the norm of f square times the norm of g square. Correct? S. It's making sense. Okay, good. And how do we write f? F we can write as the norm of f we can write as what? In terms of the inner product. Right? So this is f, correct? Exactly. So let's do ff first. Okay, so and then gg will be essentially the same. So ff is what? Ff is, again, we use this definition. Exactly. So integral over fx. Okay, I have to be a little bit careful. Was it over reals or it doesn't say? Okay, so you may need to put a bar, okay, depending on whether it's real or not. In the I don't know how they define the inner product, but you would likely need a bar, otherwise the homogeneity property won't work. Okay. So fx. So let's just say it's yeah, so for now let's assume it's real. It says real valued. I'm such an idiot. Sorry. Okay. It is real valued. Okay. So then it would be fx times fx dx, correct? Is that okay? That's the inner product. And yes, the absolute value of the inner product, which we actually don't care about now because it's like because it's a sum of positive things, so you don't have to write it explicitly. Okay. So it's fx, which is what? Fx square dx integration -1 to 1, right? So the first term is going to become what? It will become integration -1 to 1 fx square dx. Is this okay? And what will the second term be? Okay, -1 to 1 ga. Towards the edge, the pen becomes a bit wonky. Okay, right? Making sense? L? Yeah. Okay, so we wanted to bound this object. We wrote it as some inner product. We applied Cauchy-Schwarz, and then we expanded those things. The crucial thing was, of course, recognizing that you can write it as an inner product. Okay, and for this, you have to know the norm, and you have to know what vector space to use. Those are the two things. Yeah. Okay. Any questions? Good. Okay. All right. So now the next result that we're going to look at is called the triangle inequality. So it has the following geometric interpretation. It's basically saying that, so we're going to now look at the triangle inequality. And what does it say? It has so we'll write the geometric interpretation first. So geometrically, what it means is that the length of each side. My handwriting is really shoddy because stuff is already written here. Okay, I'm not writing very carefully. Otherwise, it gets very slow. Okay, so if you're not able to read it, I'm just writing stuff for me, not doing anything. So the length of each side, right, of a triangle is less than, okay, the sum of lengths of other sides. Okay, lengths of other sides. Okay, this we know very well. It's nothing new. So we're just saying that the length of this u plus v is going to be at most the length of u plus the length of v. Okay, and it doesn't have to be like there are no constraints. It doesn't have to be right angle or whatever. For any triangle, this is going to be. All right. So is this like a small consequence? It's saying from the triangle inequality, it follows that the shortest path between any 2 points is a line segment. Because the moment you deviate, the length becomes larger, right? Just from there. Right? So that's fine. Okay. So now let's see what the statement is. So proposition 6.18 says, which I didn't have to read, sorry. Okay, so the triangle inequality is formally written for the following statement. So suppose that u and v are vectors in capital V, the vector space. Okay. Then, okay, so let's draw it. So suppose there's some vector u, there is some vector v. Okay. Then the claim is that the length of u plus v is going to be at most the length of u plus the length of v. Okay. So I think I drew the vectors. So okay, so you can write these vectors as follows. Because you can write u like this, and then you can write v. I'm just moving the vector, okay, so that I can make the right triangle. If you put both of them at the same edge, then that's not really the triangle we're looking at. So you're looking at the vector u plus the vector v, and then u plus v is this one. Okay, don't get confused. If you draw it at the same point, you'll not be able to make the triangle easily. You have to transport it. I hope you know all this, but just in case. Okay, so now what is the statement? The statement is that the length of this guy, u plus v, is at most the length of this plus length of that. Is the statement okay? Yes? Is the statement okay? Well, yeah, okay. Okay, and then it says that this inequality, so and the inequality becomes an equality if and only if one of u comma v is a non-negative multiple of the other. And so it says for equality to happen, both of them have to essentially be in the same direction. They both have to point in the same direction. Then you will have u plus v. The norm is the same as norm of u plus norm of v. Okay. All right. So let's see how to show this. So let's start with the first part, right? So we want to show this inequality to begin with. So the inequality says the following. So by definition of the norm, we can write. Yeah. Let me actually make some space. Okay. So let's start. Okay. So we have u plus v. The length of the norm of u plus v is going to be what? What is the definition? It's the inner product with itself, right? So let's write it out. So the inner product with itself would be u plus v, inner product with u plus v. Just use the definition, not anything. Okay. The next step is, of course, we're going to use the linearity, right, of inner products. So how do we expand it? We write it as u plus. Okay, let's write the vv term together. And then you have the cross terms, right? So then you have uv plus uv. Is that okay? I've done nothing. I'm just expanding. All right. Now we're going to write uu plus vv. So these two terms are unchanged. And in the last step, what I'm going to do is I'm going to use the conjugate symmetry property. Okay? So I will write this as uv plus the conjugate of the same complex number. Right? All right. So we have this. All right. Now, what do we want to do, right? In the end, we want to get back to the norms, right? Okay. So we already see that this is well, this is already in that form, so we can write it as the norm of u. Correct? Is there a square or not? There is. Good. Similarly for v, is fine. Okay. Now, what can we say about this part? Can we simplify this somewhat? So remember, this is a complex number, right? So alpha plus the conjugate of the complex number is what? 2 times the real part of alpha. Is that okay? So let's write it down. So this would be 2 times the real part of. So yeah, let me not write too many brackets. U. Is that okay? Okay. All right. So far everything was an equality. Everything was exact. We didn't. So now we're going to use an equality, an inequality. So we're going to say that the real part of a vector cannot be more than the vector, the length of the vector, not the vector, the magnitude of the complex number. So the real part of a complex, so what am I saying? I'm saying that the real part of a complex number, so real part of a complex number must always be at most the magnitude of the complex number. Right? That's all I'm doing. Okay. All right. And then once we have this, now do you recall any inequality involving UV? Okay, so we learned a very nice inequality now, right? So we learned Cauchy-Schwarz. So Cauchy-Schwarz says what? It says this thing is going to be at most what? So I'll write the first terms as it is. Plus 2 times. Cauchy-Schwarz is going to tell us what? Who's going to tell me what Cauchy-Schwarz says? Is that okay? Right, we just applied Cauchy-Schwarz. We didn't do anything complicated. Correct? Okay, let's add some more space now. Okay. So right, so we have this, and now I think we'll do what you were saying, right? Now this is essentially our favorite a plus b whole square is a square plus b square plus 2a. So we complete the square, and this would give us what? It would give you u plus 1 whole square. Correct? Is it right? All right. And well, we have the inequality, right? So this is what we wanted to show, that the norm of u plus the norm of u plus v is at most essentially the norm of u plus, right? You can get rid of the square, right? So this implies u plus v is at most norm of u plus norm. Okay, congratulations, you proved your triangle inequality. Okay, all right. So now there's the non-trivial part of figuring out what happens to the in the event that you have equalities. So when do you get equality? That is the question. And for this, we'll need to reason a little bit. So let's see. So the parts that we're going to focus on are these. Okay, so we looked at the inequality arose in 2 steps. So one, it arose when we said the real part is at most the magnitude of the complex number. Right, so that was one. And the second was when we applied the Cauchy-Schwarz. Right, those are the only 2 places where we had the inequality. Correct. Everything else was equality. Okay. So yeah, maybe. Yeah, I want to have a screenshot of this. Can I copy it? Give me a second. Let me see if I can copy this thing. Oh. Okay. Yeah, otherwise it would be a little bit more difficult to sort of see what is happening. So this one is 6.19 and this one is 6.2. Those are the 2 steps. All right. So now let's try to reason. So equality holds means what? It means that both 6.9 and 6.20 are equalities, right? Because if any one of them is an inequality, then you would not get it. Correct. So both have to be equality. And it's if and only if, of course. Is this step okay? Yeah? S. S. Is this step okay? Which step am I talking about? Okay. So I'm just saying that we are trying to show that equality holds, right? So equality in what? In this statement, we're trying to understand when does equality hold. Okay? to get equality, we are saying that both of these steps have to become equality. That is all I've said so far. Okay. Is it okay? Yes. I don't know if you're. I can repeat if you're lost. Where did you get lost? Tell me. 6.21. Yeah. We haven't gotten there. We're still here. So we haven't gotten lost. Okay. Let me kill this and start. Give me a second. Yeah, it's okay if you. It is a long 1.5 hour class. It's normal that your mind wanders. If you get lost, tell me and get back with the class. Okay. Otherwise, you lose the time you're spending here. Okay. So right. So here's the equality. Oh, come on. It's got the same problem. No, it's not. Sorry. So okay. So we want to know when this equality is strict. And all I'm saying is that this equality would hold is equivalent to saying that these inequalities, these two steps that we assume, they're equalities. That is all I'm saying. Everyone with me. L. Yeah. Okay. So now, if these two things are equalities, that is equivalent to saying, and this is sort of the delicate part. Okay. It is equivalent to saying that the inner product of uv is exactly the norm of u times norm of v. Okay. So what is it saying is that if these two things are true, if these two inequalities are true, they are actually equalities, then from this you can deduce that the inner product must be the norm of u times norm of v. Okay, and this statement is not so obvious. Okay, so we're going to try to reason about it. Okay, the opposite implication is easy. We'll leave this as a homework. Okay, so if you know that this statement is true, it's not that hard to check that 6.19 and 6.20 are going to be true. Okay, that's the easy part. Let's do the difficult part. So the difficult part is, you know that these two inequalities are equalities. How do you show that this is going to be 6.21 is going to be true? Okay, so let's see. So 6.20 says what? So 6.20 says that the norm. So this is an equality, right? So what does that mean? That means that uv is the same as, right? Because these two terms will cancel, right? When you enforce 6.20. Is it making sense? So if you enforce 6.20, you're getting that norm of u square plus norm of v square plus 2 times absolute value of uv is the same as norm of u square plus norm of v square plus 2 times norm u norm v, right? So I'm just canceling these guys and saying this would. Is that okay? Right? So you have this step. So we have that. What is 6.19 telling us? So 6.19 is telling us by essentially the same argument that 2 times uv, we can also drop the 2 side. We don't need 2. This is going to be the same as the real part of uv. Correct? That's fine. It's exactly the same argument, right? So you will cancel these guys, and then you'll be left with, you can cancel the 2, and then the real part is the same as. Okay. All right. So what does that essentially tell you? Once you have this equation, it tells you that uv is the same as the absolute value. Right? Because if a complex, the norm of a complex number is the same as the real part of the complex number. This is fine. Right? Okay. So we have this part. And you can just combine them now, right? So you already had this in the previous expression. You can substitute it and get uv is the same as norm u times norm u. Correct? And that's what we wanted to show. Is that okay? You got lost. Where did you get lost? Tell me. So, okay, this step 1, step 2, and step 3. So step 1, was that okay? Yes or no? That was fine. Okay. Step 2. Step 2 is applying the same argument, just like we said, these two are the same, right? Using 6.19, we are saying these two are the same. Right? So let me write it again. So 6.20 implies that norm of u times norm of v is the same as inner product of u and v. Right? And 6.19 is saying what? This implies that the real part of uv has to be the same as the, right? And now we're going to use the fact that the real part of a complex number is this. If you know that the real part of a complex number is same as the magnitude, this implies that the magnitude of alpha is the same as alpha itself, essentially. Because it's like a plus ib, right, is the same as a square plus b square, whatever, square root. So you're just concluding that. So if just the real part, sorry, if a is equal to a square plus b square, b has to be 0, basically, right? That's all. Hmm? Yeah, but here you have the real part. Am I doing something wrong? So it will automatically be positive, right? Because the real part is a, right? So a has to be positive because a is equal to something positive, right? If you have that cannot be right. If the real part is equal to something positive, the real part cannot be negative, right? That is the whole point. So the real part of alpha is some positive number. So the real part cannot be negative. Okay. So that's the point. So you get this, yeah. Okay. And then once you have this, that would mean that I may be slightly wrong. You can check. These are things that I also figured, but if I'm wrong, you can figure it out. But this should be the case. So this would mean that you can. So from this you can conclude that.
So we explain why A has to be non-negative.
Oh, because the real part of alpha is non-negative, right?
What of alpha has to be
And then uv is the same as right. So here uv is the same as the absolute value of uv. Yeah, this is so inner product uv is what? It's a complex number, right? So when you write mod is how you this is the same as the way you define for a complex number. Yeah. No, but you have this equation, right? This equation is saying that the real part of alpha is a positive number. Right? This thing cannot be negative, right? So if this equation is true, right? This equation forces you. So real alpha, in general, it can be negative, right? But if this is equal to mod alpha, this is in particular greater than equal to 0, right? Sure. Mod alpha can be negative, but you're concluding that real alpha is non-limited. You're using this to get this fact, and then from there you're getting real. Okay. Is that okay? All right. So finally, what we're getting is that the inner product of UV is the same as the norm of inner product of UV. Okay. Is that okay? Just from all these elements. Okay. And from 6.20, we already had the fact that norm of V is equal to the absolute value, but we just argued that the absolute value can be removed from this is equal to U. Correct? Is that okay? All right. So finally, where do we get? So we are able to show 6.21, right? This is exactly what we wanted to outline. Is that okay? Is it okay? Making sense? S? You guys are fine this week? L? Okay, all right. So now we're almost done, essentially. So now we have to use these conditions to conclude that U and V are non-negative multiples of each other. So we have to conclude U, V are, so this is what we want to conclude in the end, right? U, V are non-negative multiples of each other. So remember, we were worrying about the sign because, for the statement to make sense, right? So remember this picture, right? For this statement to make sense, that the length of U plus V is exactly the same as U plus V, the vectors have to be in the same direction. Otherwise, the statement won't. So that's why we're worrying so much about getting the sign to match. Okay, that's important. Okay, so all right. So we want to show it. So this is what we want to conclude. Okay, so want to conclude that for UV, UV are non-negative multiples of each other. Okay, this is the statement that we want to make. So how do we do this? Okay, if one of UV is a non-negative multiple of the other, then 6.21 holds. So we are assuming, so we're going to do it in both directions, up and down. So for the first direction, we are saying suppose UV is or are non-negative multiples of each other. Okay, so suppose this is the case, then one can verify that the inner product would be UV is going to be the same as okay. Why is that? So suppose let's do it explicitly, right? So suppose U is say C times V. Okay, and C is non-negative. Right? When you take the inner product, what do you get? You get CV times V. And then you can check the rest. Okay, so the crucial thing is this is non-negative. Okay, all right. So this part is fine. Now let's do the other way, right? So suppose that you're given that 6.21 is true. So what was 6.21? You're given that the inner product of UV is norm of U times normal. Okay. So suppose you're given this. Now we want to conclude that U and V are non-negative multiples of each other. That's what we do. Okay. So recall the equality condition 6.15 in Cauchy-Schwarz said that U and V are scalar multiples of each other. So Cauchy-Schwarz, remember, was saying what? It said that when is the Cauchy-Schwarz inequality saturated? It is saturated when the vectors are scalar multiples of each other. Right? That we proved that just a few minutes ago. Okay. All right. So clearly, this forces the scalar to be non-negative. Okay. So from Cauchy-Schwarz, we deduce that there has to exist some scalar. And from this condition, we conclude that this scalar has to be non-negative because it's a product of non-negative. Okay. So you conclude that the thing that for the triangle inequality to be saturated, the vectors have to be a non-negative scalar multiple of each other. Okay, so the important thing is non-negative. Is that okay? Is it okay? Did you get lost somewhere? Tell me. You don't seem convinced. So okay, so was this step 3 clear? First of all, let's backtrack. So step 3 was fine. Okay, so step 3 is fine. Now what we're trying to argue is that suppose this step 3 is true. Okay, so we're trying to argue. Let me write it down maybe somewhere. So suppose you're given that the inner product of UV is the norm of U times normal. Okay. So now what we're going to do is we're going to recall that what did Cauchy-Schwarz tell us? So Cauchy-Schwarz said that Cauchy-Schwarz is saturated. Saturated meaning like the inequality is equality when the vectors U and V are scalar multiples. Right? This we proved a few minutes ago. Now the point is that we are also given that the inner product of UV, right? So okay, so suppose it is so let me write, so therefore U is say C times V. We don't know whether C is negative or positive, correct? This way. So now we can use the third equation that we had. So if you substitute this, what do you get? You get C times VV is something positive or something non-negative. Right? And can this thing be negative? From the inner product, it cannot be, right? The inner product of any vector with itself is non-negative, it's the definite process. So this is also non-negative. But that's what we wanted to show, right? We just wanted to show that U and V are non-negative scalar multiples of each other. Yeah. Okay. All right. Hell, is it okay? Well, we only have 10 seconds anyway, so you can ask me later. It's not. Okay, yeah. So I think we can stop here, and next time we'll look at this parallelogram equality and some fun things. Okay. Thank you so much, you guys.